Hey Honors Physics, this is Mr. Hausman. We're going to be taking a look at the next level of detail having to do with simple harmonic motion. And specifically, we're going to be looking at displacement versus time graphs for oscillators. Now, what kind of oscillators are we referring to? We're, of course, referring to pendulums. They come in many forms, or also a new kind called mass on springs. When you take a mass and you hook it up to a spring, it can be linear or it can be vertical. And as long as there is minimal friction with the air or with the surface, what happens is, of course, they bounce up and down. Very much like how a pendulum swings back and forth. Now, do you notice, I'm going to draw a little line, they seem to go through a range of motions. These are where the spring is maximally compressed. Here's where the spring is maximally lengthened. And what that means is that there's a middle point or an equilibrium. And that's kind of like how a pendulum goes through the equilibrium position at the middle. Right? The equilibrium is here. Now, what they have in common is that they both have amplitudes. The amplitude is measured in theta for a pendulum, and it's measured in x for a spring, meaning what's the distance from the equilibrium position. But the concept of energies applies to both of them. We have potential and kinetic energy transformations going on for a swinging pendulum as well as for a mass on a spring. Okay, so here's the new kind of graph, a displacement versus time graph. Displacement is on the y-axis, time is on the x. And what you'll notice is that it resembles, some of you are very familiar with this, a sine or cosine graph. And that's great. That means you can actually do calculations and predict formulas for how this might work. But really what it is one or two-dimensional motion bouncing up and down, and then you measure that change in position as a function of time, and you notice it repeats itself. So whenever the object is farthest from its equilibrium point, right, that middle, we refer to that as an amplitude. Here's an amplitude. Here's an amplitude. But also an amplitude can be measured on the other side. How far is it to the lowest or farthest position on the other side? So amplitudes are always kind of half the height of the wave or from the midpoint to a maximum displacement, right? We would call this a max displacement. You can measure the period from crest to crest or from trough to trough. This would also be a period. But I bet you can also imagine that this wave not just repeats from crest to crest and trough to trough, but anytime the wave is going through a full cycle. So as it goes up to one extreme, maximum displacement, comes back to the equilibrium, then it goes to the other maximum displacement, but in the other side, the negative side. And so you could actually say that one period is from A to I on this graph. There's many ways you can kind of depict that. Okay, so it repeats at a constant frequency. We've already mastered that, right? The frequency and the period of a swinging pendulum has to do with the length and gravity. We discovered that in lab. Now, the other key idea is that there has to be a restoring force and an acceleration. And they're always away from the displacement, meaning they are toward the equilibrium. That's in fact why we can't swing a pendulum much past 20 degrees and maintain simple harmonic motion, because then the forces that restore it are not toward the middle. And it does tend to become less periodic, less predictable. So let's talk about two key variables. Let's talk about velocity and kinetic energy. Where are they at their maximum? Well, they're going the fastest when you go through the equilibrium position. And therefore, if you have a high velocity going through the midpoint, you also have maximum kinetic energy. It's zero velocity when you're at extreme positions, right, farthest from the equilibrium, right, at the two maximum displacements. So let's talk about how displacement changes, right? Displacement is really related to potential energy. The maximum or extreme position for your displacement is when you're farthest from the equilibrium, and so you have a lot of potential energy on the far extremes. And you'll have zero displacement and zero potential energy when you go through the equilibrium. So now we're going to make a table that kind of summarizes that. Let's open this up a little bit. So let's find and label whether the variable is maximum or zero, like maximum or minimum, and whether the variable is increasing or decreasing if it's going through a transition. So for example, at position A, where is that? That's all the way over here. We've got position A is at a maximum displacement. So let's do that. Let's write in maximum displacement. Well, don't we know that when you have maximum displacement, you also have maximum potential energy? See how they're linked. The farther you are away, the more energy you have stored because you're higher up in this case. Now, at the same time, you have zero velocity and you have zero kinetic energy. Okay, I get that those are linked. Let's talk about the restoring force. Well, the restoring force and the acceleration are always proportional back to displacement. When the displacement is maximum, the force restoring it is also greatest. So we've got a pattern here that reads max, zero, max, zero, max. That's really a coincidence that they kind of alternate like that, but really just the idea that each of these quantities is linked to another. Displacement is linked to the kinetic energy. Displacement is linked to the potential energy. Velocity is linked to the kinetic energy, and the force is also linked to the force. Okay. Now let's go to position B. B is not the next position over. It's right here. It's maybe a little more than halfway down. It's got a smaller angle between it. So its displacement is decreasing, right? The angle for A is much larger. The angle for B is smaller. So that's a decreasing displacement. Its velocity is increasing. And now let's link to the fourth and fifth columns. So if you're increasing your velocity, you're increasing your kinetic energy. If you're decreasing your displacement, you're decreasing your potential energy. And since force, the restoring force, is proportional to displacement, that's also decreasing. Okay, where's C? C is the middle position. So you have zero displacement and you would have zero potential energy, but you would have maximum velocity and maximum kinetic energy, and you'd have zero restoring force. Let's examine why. The only force on this pendulum as it swings through position C is the force of gravity and the tension. And see how neither of those forces are pulling you back toward the middle. Your inertia carries you through position C. D, on the other hand, we have a decreasing and therefore decreasing potential energy. We have a, oops, that's a mistake. Let's go back. I regret that. We have an increasing and therefore increasing potential energy. As soon as I said it, it didn't sound right. We have a decreasing velocity because we're slowing down as we swing up, and we have a decreasing kinetic energy, but we have an increasing force and acceleration. It is still a force and acceleration. Now you may say, but I thought you said it was slowing down. Well, the force that's restoring it is back toward the middle. It would actually be a larger negative acceleration that's building up as you swing. I'm going to let you finish E, F, G, and H to see if you can continue the pattern. Hit pause, fill in the rest of the table, and then I'll check. So if you just finished, you will notice that the pattern continues. So now we're going to finish with masses on springs and put together or pull together some notes. So we already have the idea that they have a displacement and they have energy when they bounce up and down, but the maximum amount of amplitude is when they are the maximum amount of distance, and we don't measure it in angles anymore, we just measure it in distance, in meters, from its rest position. And the symbol in equations is an A for amplitude. Frequency, we should already be familiar with that. How many cycles or bounces per second? And the symbol, of course, for frequency is an F. It's measured in hertz. Let's keep going. Period, time of one bounce or one full cycle, and that's T. And there's a new formula. Sorry, that should be an uppercase T. Bad pen work. And T is now equal to 2 pi times the radical of mass over the spring constant. So we have it. And so we have, to kind of refamiliarize ourselves with it, right? So the symbol is K, and its unit is how many newtons does it take to stretch a given spring a meter. Even if you can't stretch it a meter, it's still the units, okay? It's a ratio of force to distance. Mass is, of course, kilograms. And now, let's kind of review some of the things that we've already examined with swinging pendulums about force and velocity. So when does a spring, mass on a spring, have the greatest force, right? When it's maximum when it is farthest from the equilibrium position. So if the equilibrium position is where it has not been stretched or compressed, here we would have a maximum displacement, and we would have the spring pushing back toward the middle. Here, at the far maximum displacement, this mass, now the force of the spring is back toward the middle. And that's referred to as, of course, a spring force. And we learned about that a little bit earlier in the year. We didn't do as much with it, okay? The force on the other hand, let me try that again. The force and acceleration is 0 at the equilibrium point. There is absolutely no force on the spring because the spring is in its relaxed position. It may not look it that way, but this spring has been manufactured so that it looks like that when it's at the equilibrium. Finally, right, velocity is maximum when it goes through that equilibrium point because it's bouncing, it's building up speed when the force pushes on it, and then it is 0 velocity at the far extreme. This is definitely a page that has to be digested or consulted or checked it with as you're working on problems. And that leads, oops, there we go, to calculations. And we're going to do one of them together. This is going to benefit people who weren't able to be in class due to an AP and they want to have another resource, or anyone who just wants to see it again. So new formula having to do with masses on springs. It calculates the period, and therefore you could get the frequency from it. And now the formula is 2 pi times mass over spring constant under the radical. So how would you set up a typical problem? T is equal to 2 pi radical m, 0.5 kilograms, over a K value of 10 newtons per meter. And when you multiply that out, you're going to get 2 pi times the square root of 0.5 divided by 10, close the parentheses, and I get a period of 1.4 seconds. And that's pretty much how hard they get. Sure, I could ask you to solve for the unknown mass. Honestly, I could ask you to solve for the unknown mass. I could ask you to solve for the unknown K value of a given spring. But that's pretty much the beginnings and kind of a closure on simple harmonic motion having to do with, of course, pendulums as well as springs.